Good evening, everyone. My name is Sean Simpson, and I'd like to welcome you back to another Tech Talk in our series sponsored by Seismic. Today, we have the pleasure of welcoming Howard and Karol to give us a brief talk about Kubernetes and Docker Swarm. So without further ado, I'll pass it on over to you guys.
Thank you, Sean. I would like to thank Seismic for sponsoring our Tech Talk. Tonight, we're going to be talking about Kubernetes and Docker Swarm. I'm Howard Sun.
And I'm Karol Krzywon.
The topics we'll go over are what are containers, Kubernetes overview, Docker Swarm overview, pros and cons of each system, which solution is right for you. And to understand Kubernetes and Docker Swarm, it's essential to start with the foundational concepts of containers. A container is a lightweight, standalone executable package that includes everything needed to run a piece of software. The code, a runtime, libraries, environmental variables, and config files. And this encapsulation ensures that the application runs uniformly and consistently across different environments. Containers are not just about packaging. They also offer a degree of isolation due to the Linux kernel features like namespaces and C groups. This isolation, while not absolute, provides a secure and efficient runtime environment for applications. Each container runs as its own isolated space with its own processes, networks, interfaces, storage, and yet they use the host kernel, and this sharing minimizes overhead and maximizes resource utilization. In the context of Kubernetes and Docker Swarm, understanding containers is crucial. And containers enables the system to have high availability, scalability, and management of applications with ease. So as we move forward to explore Kubernetes and Docker Swarm, remember that the heart of these powerful orchestration tools lies the concept of containers. Kubernetes also means captain, if anyone's wondering. And here we have a diagram for the Kubernetes cluster. This is essentially the admin UI, the control plane, the worker nodes. And if you are having difficulties, you can abstract that away by using a managed Kubernetes service offered by Google, Amazon, and Azure. In our admin tools, there are the admin UI and the command line interface, and these are both essential for developers and system admins to provide a seamless experience in deploying, scaling, and maintaining applications. In the web-based environment, it serves as a visual platform for managing Kubernetes clusters. It offers a comprehensive overview of running application with the cluster, allowing users to easily identify state of deployments, the stateful sets, and more. One of the standout features is its capability of scaling deployments, initiating rolling updates, and restart pods from the interface. The level of control and visibility is invaluable for maintaining the health and performance of applications. Additionally, the admin UI provides real-time insight into state of Kubernetes resource and highlights any errors that may have occurred. In parallel to the admin UI, there's a kubectl, which is the command line interface, and is a powerful tool that communicates with Kubernetes clusters with Kubernetes API, which is a RESTful interface. It allows users to execute a wide range of commands for managing applications and modifying cluster state. As we dive deeper, we have the control plane. And within the control plane is essentially the brain of the Kubernetes cluster, making decisions about the cluster state, ensuring that the actual state matches the desired state. At the heart of the control plane, it is an API server. It's a central hub for all cluster management operations. It provides a RESTful interface, allowing for management and control of the cluster through a wide range of operations. The API server ensures that all operations are authenticated and authorized, maintaining security and integrity of the cluster. It communicates with etcd, which is a highly consistent and highly available key value store used by Kubernetes backing store for all cluster data to store and retrieve the cluster state. Additionally, it also interfaces with the scheduler and controller management to manage application deploy, scaling, and overall health of the cluster. Then there's the scheduler, also within the control plane. It continuously monitors workload on pods, assign loads on newly created pods. The scheduler is responsible for scheduling pods on specific nodes based on automated workflows and user-defined conditions. such as resource request, affinity, tolerances, priority, and persistent volume. This ensures that pods are placed in the most optimal location and balances resource utilization with application performance. And then there is the controller manager, which plays a vital role in managing the cluster. It runs various controllers, including node controller, job controller, and among others, which helps maintain the cluster's health, ensuring smooth operations. Controllers are responsible for noticing and responding to changes in the cluster, such as node failures, replicating pods and managing endpoints and service accounts. Overall, the control plane is at the core of Kubernetes, responsible for scheduling, creating, and managing containers across cluster nodes. It maintains a communication with worker nodes and ensuring that the cluster operations as a cohesive unit. And for high availability within Kubernetes, it's recommended to have at least 3 control plane nodes in each different regions with components replicated across them. This ensures that the cluster remains operational even in the events of a node failure. And we go to nodes. Within the nodes, we have pods, which is the smallest deployable unit in Kubernetes. A pod is essentially a group of one or more containers that are tightly coupled and shares a same network namespace. This shared network namespace means that all containers within pods can communicate with each other using localhost, facilitating efficient inter-container communication. The use of a single IP address for all containers in a pod simplifies the networking and seamless integration of microservices. Additionally, in the node level, we also have the kubelet, which is an agent that runs on each node in the Kubernetes cluster. The primary responsibility of a kubelet is to ensure the container within a pod are healthy and running as expected. It monitors the containers and manages their lifecycle and reports the status back to the control plane. This ensures the application running within the pods are always in the desired state, providing a reliable and consistent runtime environment. Another critical component in each node is a kube-proxy. It is a network proxy that plays a crucial role in implementing parts of the Kubernetes service concept. It maintains the network rules in the nodes, ensuring oncoming traffic into a node from a service is forwarded correctly into the appropriate containers within the cluster, and the Kubernetes achieves this by using the OS packet filtering layer, such as IP tables. So in essence, the pods, the kubelet, and the kube-proxy form the backbone of Kubernetes and enables scalable, distributed, and resilient application deployment management. And these are the major parts of the Kubernetes architecture. And we're moving on to Docker Swarm.
Thank you very much, Howard. Now, for the second half of this presentation, we'll be diving into Docker Swarm, which is Docker's native clustering and orchestration tool. And kind of like the image on the left shows you, it does share similarities with Kubernetes. However, it does offer some key simplicities that might benefit others. So let's dive in. So to start off with, Docker Swarm is seamlessly integrated with the Docker engine, making it incredibly straightforward to set up and use. It's designed to support both manager and worker node roles within a cluster, ensuring that your applications can scale effectively and maintain high availability. And overall, it contains an advanced feature for managing a cluster of Docker daemons, ideal for production runtime environments. As I mentioned earlier, it is built into the Docker engine, distinguishing it from previous iterations, sometimes now referred to as Docker Classic Swarm, which is no longer actively developed. So with that, let's explore how Docker Swarm simplifies cluster management and why it's still a powerful tool for deploying containerized applications by delving into some of its core features. So Docker Swarm offers a declarative service model, allowing us to define the desired state for our services. It then works tirelessly to ensure the actual state aligns with our defined state. When it comes to scaling and load balancing, Docker Swarm enables services to be scaled based on demand and efficiently distributes incoming traffic across containers. However, it's important to note that automatic scaling requires third-party tools for monitoring and management. Docker Swarm also excels in service discovery and networking, providing built-in mechanisms that facilitate easy communication between containers. It supports rolling updates and rollbacks as well, allowing us to update services with zero downtime and to revert previous versions if necessary as well. And its advanced networking features include overlay networks, ingress routing, and service-to-service communication, enhancing the flexibility and efficiency of containerized applications. Now, with these features in mind, let's take a closer look at the exact architecture that makes all of this possible. So at the heart of Docker Swarm is the Swarm mode, which truly reflects, if not quite ambitious or very creative, at least reasonably sound and consistent naming practices. Swarm mode, which includes essential components for node management, task scheduling, and service definition. The architecture is built around two types of nodes: manager nodes and worker nodes. Manager nodes orchestrate the cluster's operations and maintain its state using the Raft consensus algorithm, while worker nodes execute the tasks assigned by the managers. These worker nodes can also be grouped together as what's called a gossip network, which is employed to enhance communication and fault tolerance. The roles and responsibilities are explicitly defined, with manager nodes acting as the brain of the swarm and the worker nodes serving as the muscles. And with Docker Swarm's decentralized design, it allows for the deployment of both the manager and worker nodes using the Docker engine, enabling the building of an entire swarm from a single disk image. So with that, let's look into more what Docker Swarm achieves high availability and fault tolerance as well. So Docker Swarm ensures high availability through manager nodes redundancy, utilizing multiple manager nodes to prevent a single point of failure. That Raft consensus algorithm plays a crucial role here, requiring a majority for decisions and keeping the cluster operational, even if some managers fail. And in the event of a leader manager node fail, Raft ensures a new leader is elected, allowing the cluster to continue functioning without interruption. Another key feature is task rebalancing, where Docker Swarm automatically redistributes tasks to other available nodes to maintain the desired state of services. Scalability is also further enhanced by its ability to automatically adapt by adding or removing tasks whenever you do scale up or down. Now that I've given you a bit preview of Docker Swarm, let's do a little comparison between the Docker Swarm and Kubernetes. So Docker Swarm is known for its simplicity and ease of use, making an excellent choice for smaller scale deployments. It's built right into Docker Engine, allowing you to create and manage a swarm of Docker nodes as a single virtual Docker host. Features like service discovery, load balancing, and rolling updates are all part of Docker Swarm's offering. And it's designed really with that ease of use in mind, making a preferable choice for simpler applications. It's lightweight, tied with the Docker API, which does limit its functionality compared to Kubernetes. And its automation capabilities are not quite as robust as those offered by Kubernetes, which might be a consideration for more complex applications. On the other hand, Kubernetes is an open source platform originally developed by Google, designed for automating deployment, scaling, and management of containerized applications. It supports automatic scaling, self-healing, load balancing, and rolling updates, among many other features. And it's really well suited for complex applications, offering a rich ecosystem and a large community, making it the most widely adopted container orchestration platform. Its robust automation capabilities and support of various container runtimes, including Docker, make it a powerful choice for applications with high demand or complex configurations. So which solution is right for you? Well, if you're looking for a quicker and simpler setup, Docker Swarm might be the way to go. It's built into Docker Engine and is ideal for getting a simple application up with a very short learning curve. It's also perfect for those just getting started with anything to do with containers, especially when deploying them into production, offering a seamless fit with other Docker products and a straightforward setup process. Its declarative configuration and lightweight nature make it easy to get started for those already familiar with Docker. However, if you need more robust features, rapid scalability based on traffic, and support from major cloud vendors, Kubernetes then might be the better choice. It's well suited for those applications with high demand and complex configurations, as I've mentioned, and offers really advanced automation features, a high degree of customization, and a really comprehensive solution for deploying and managing containerized applications. So with that said, I'd like to open up the floor for any questions. All right. If there are none, here are our works cited. And if you'd like to find out more information, please feel free to reach either Howard or myself. We have our LinkedIn's, Gits, and emails all up on the slides. And of course, I'd like to thank Seismic and our other sponsors for making all these tech talks possible.
Well, thank you guys for that informative talk. And thank you everyone for coming out tonight. We'll see you at the next one.